Hello, everyone. My name is Xuebin Wang, a PhD student from Applied Math department. And our group is one of our group's interests is to develop efficient and robust solvers for partial differential equations. And today I will show you what we developed to solve the time integration problem for time-dependent PDEs. For time-dependent PDEs, we need to solve the solution step by step in a discretized time span. And between each steps, we need to do the time integration. And Runge-Kutta schemes are most commonly used to solve the time integration problems. As we said, it is a kind of integration. So general Runge-Kutta schemes can be treated as to do some kind of integration by quadrature points and quadrature weights. And the main focus to solve this problem is to choose the proper Runge-Kutta schemes and to solve the staging vector we need to add the quadrature points. And Runge-Kutta schemes can be classified into two groups, like explicit schemes and implicit schemes, depending on the shape of the schemes. For explicit schemes, we can solve the staging vector step by step because the shape of the scheme is just lower triangular and with the zero diagonal entries. But for implicit schemes, we need the shape of the Runge-Kutta schemes is a full matrix, so we need to solve all the staging vectors at the same time. But there is a disadvantage of explicit schemes, that it has a limited stability region, which means if we choose the time step to be relatively large, it will get out of this stability region, and the solving process can be done. And so that is why we choose to use implicit Runge-Kutta schemes, because we have an unlimited region to choose our time steps, so it can be relatively large. And another advantage is that to achieve high order of accuracy, like if we want a fourth order of accuracy, then we need only two stages. We need to only solve two staging vectors with implicit Runge-Kutta schemes, but we need to solve four staging vectors use explicit Runge-Kutta schemes. So since we think there are so many advantages of implicit Runge-Kutta schemes, so we turn to the challenging problem, that how do we solve the staging vector at the same time? So suppose we have three stage, then we need to solve a number of degree of freedom times the three stage, and this kind of unknowns at the same time. For this large scale system, we propose to use the product subspace method to solve it. And it is kind of an iterative solver, and it is much more efficient, but it requires a good preconditioning method. We develop our preconditioning method in this order. We first develop our preconditioning method for linear case, like a linear parabolic equations, and then generalize our preconditioning method into nonlinear case. Why we do it? Because for linear case, the system to solve the staging vector has a kind of a Kronecker product structure, which we can take advantage of, and we can do Schur decomposition for the Bush array, and do our multi-level factorization for the blocks on the diagonals. So with our dealing with the Kronecker product structure, the system can be solved in a mathematical optimal way, and from the results, it outperformed outperform the state-of-the-art preconditioning methods. And to do and then we generalize our solver for linear parabolic equation to nonlinear parabolic equations by doing the Newton's iterations for the nonlinear systems, and iteratively solve the augments so that we can converge to the final solution. And to solve and in the process of solving the augment in each Newton steps, we also we can also use a generalization of our preconditioning method for linear case and get good performance in both time of solving and number of iterations for the follow subspace method. Yeah. So this is what we propose today, and thank you.
I don't know what's going on. So you use the word optimal there, and so in what sense are these preconditioners optimal?
We call it optimal because in the linear case, if we do not, what we do is the incomplete high multi-level factorization for the diagonal blocks. If we do the complete factorization for the diagonal blocks, it can converge in only one step. So that is why we call it optimal. But in the most case, because the system can be in not well proposed or something like that. So we need to do the incomplete multi-level factorization for the diagonal blocks. So that is why we call it optimal.